Okay, please welcome my colleague and friend, Andrew Alexander, who for a number of years was teaching at the same school as I, and he's moving on at this point, but he has some fun activities to show us that he's been doing in his classes. Thank you.
We're still colleagues for 3 more days, technically, Ted. And then we're going to be at Deep Springs for the spring semester. Anyway, good morning. It's great to see all of you. I've been doing a lot of off-trail hiking recently, the last few years. This is a shot from Wyoming last summer. This is like a 13-day solo backpacking trip I did that was basically all off-trail. Just kind of wandering around the Wind River Range with a map and a compass and curiosity. Hiking off-trail is pretty hard. It's pretty slow, it's inefficient, but what you gain, and the reason I've gotten so into it, is a lot more intimacy with the landscape, a lot more understanding of the terrain, its texture, its shape, how to move your body through it. You don't just see the view from the summit, although hopefully you get that as well. You get to engage with sort of the whole environment. And so, of course, I've been thinking about math teaching as well in this context. Because when we teach math, we tend to stay on trail. We teach proofs as fait accompli, as sort of careful chains of logical deduction from assumptions to next step to next step to next step to next step, following a trail that someone else has blazed, rather than bushwhacking. And if you're just trying to get to the summit, then maybe that's more efficient. And hiking is hard, even if you're on a trail. But if you actually want to understand the landscape as fully as possible, and not just get the views, then the false paths are just as important as the true paths. And the trails that dead end teach us just as much as the trails that reach the summit. Not a new idea, and I think this is an idea that probably most of us in the room are basically on board with, so I'm not going to belabor it too much, although if you're not on board with it, I'd love to hear more in the discussion. But what I do want to do is just give 2 sort of very concrete, quick examples of times from when I teach single variable calculus and we, bushwhack around a bit, go off trail. Times when we maybe go a bit more slowly, a bit less linearly, a bit more haltingly. But as a result, I think get a better understanding of the underlying mathematics. So just 2 quick stories. The first one about the power rule, proving the derivative of x to the n, which is a story of sort of progressive refinement of a proof of a set of ideas. And then the second story, deriving, proving Taylor series, which is a story about making a lot of false starts before finally getting across the pass. So, first example, the power rule. You take the derivative of x to the n, it's nx to the n minus 1, and why is that? So, you're a kid, you're taking single variable calculus for the first time, you're playing around with Fermat's difference quotient or whatever, calculating derivatives from first principles, and doing everything by hand, and you start to notice a pattern. Derivative of x squared is 2x. Derivative of x cubed is 3x squared. Derivative of x to the 4th, 4x cubed, so on and so forth. And so it seems, at least empirically, that the derivative of x to the n is just nx to the n minus 1. So it seems. 3 pieces of evidence. But your math teacher, who's maybe a younger version of myself, says, well, that's not a proof. That's not mathematics. 3 pieces of data is not enough. We need a proof. We need something that's formal and serious and rigorous and bomb-proof. And so he shows you something that maybe looks like this. And you get very sad because you had your, wonderful conjecture that you were pleased with. You had calculated all these things, They sort of made sense. You can see the pattern. And this thing, if you're a kid learning calculus, probably doesn't make sense. I mean, what's going on here? We've got, these big iterated sums, which, theoretically, you're learning calculus. You've probably seen these before. Maybe, not necessarily. Do you have a lot of facility with them? Probably not, honestly. You've got these binomial coefficients, which, again, maybe you've seen those, but are you deeply comfortable with them? Probably not. And even if you are, there's just so much going on together. This is an overwhelming set of symbols. And yeah, it's a lot. We come from this nice clarity to this big, scary proof. That's a lot. So what I've been doing more recently, when I've been sort of walking through this argument with kids, learning the power rule for the first time, is not immediately diving into something like this, which is very tempting. It's what I did when I was younger. I dive straight into this and try to explain all the pieces, but rather sort of get to this proof in a bunch of successive passes. Where sort of the metaphor in my head is, if you think of a image on a web page that's sort of downloading progressively, rather than download one pixel at a time. You get the blurrier version, somewhat less blurrier version, sharper version, a bunch of separate passes as opposed to this one linear chain. So I've done this, and I'll show it here in 3 takes. Take number 1 on getting this proof comes from the observation that we've got this pattern here in the result. We've got this pattern in the derivatives, which means there's probably a pattern in the way we get to that. And if we can see what the pattern is in the process, not just the pattern in the result, if we can see the pattern in the process, then that's basically a proof. That's basically a solid argument. So let's go back, recalculate all 3 of these derivatives, sort of simultaneously, and see if we can spot the pattern in what's going on. So if we want to calculate all 3 of these derivatives, we start with something like this. I don't really use limit notation at this point when I teach calculus. It's a little bit more hand-wavy, but we've got these difference quotients. Derivative of x squared is x plus h squared minus x squared over h, x cubed, x to the 4th, 5th, etc. And we take those and then expand those out, which algebraically is kind of the crux, and get something like this. And I'm cheating here because I know where it's going, and so I've color-coded it, so I feel a little bit bad, but just imagine those don't have colors. We expand these binomials, we get something like that. And you're a kid in calculus, maybe you know Pascal's triangle or stuff and can expand them. Maybe you're just grinding through by hand. I've been, I guess, lucky to have kids who are happy to grind through algebra problems and will cheerfully expand x plus h to the 5th, which is great and it's good practice at a lot of things. But you do a lot of work, you feel very invested, you get something like that. And then let's see what's going on here. We've got x squared and minus x squared. We've got x cubed and minus x cubed. We've got x to the 4th minus x to the 4th. So those guys are all going to cancel. And we get something less like that. And then we've got all these fractions. We've got the h on the bottom so we can divide through. And we're going to end up with something like that. 2x plus h. 3x squared plus 3x8 plus x squared, all those things. And then as we actually do the magic, taking the derivative step, make h really, really small, send that to 0, and we end up with just 2x, 3x squared, 4x cubed, 5x to the 4th, and so on. So those are our derivatives. And so we can kind of see, if we're doing all these guys simultaneously, how the pattern is coming out, not just in the result, but in the process. We're expanding these things. The first term, the leading term, is getting canceled out. All these h powers are going down by 1, and there's that sort of magic second term, which is sort of the term that turns into the derivative. And that's sort of like trying to describe what's actually going on algebraically as we're getting this result. So then we can give this another shot and actually like try to describe that pattern. In all four of these examples, we're trying to take the derivative of x to the n, something like that. We started with something like x plus h to the n minus x to the n over h. Expanded it and got something that looked like x to the n plus nx to the n minus 1 times h plus a bunch of other cross terms that we ended up not caring about, minus x to the n over h. Those leading terms canceled, so we ended up with just that. Divided through the h's, so we ended up with just nx to the n minus 1 plus a bunch of other cross terms, and all those other cross terms still had at least one h, and then send that to 0, and we get nx to the n minus 1. And this version, actually, I really like. I think this is like, actually like, I don't know, very clear, thorough sort of explanation of what's going on with the algebra at a level that, you know, if you're an introductory calc student, is sort of like describing the patterns, describing the process without being sort of overwhelming in the symbolism. It's getting the ideas across. We're using English, which I think is underrated pedagogically in math. But if you want to keep going, if you want to up the formalism even more, you can do that. We started with x plus h to the n minus x to the n over h. And if you want to expand that and actually like symbolically write out what that would look like, then you can toss in some big, fancy, iterated sums, binomial stuff, all that stuff. And now, like, if you've seen these first two versions and have like understood the first two versions, then it makes this a little bit less intimidating. Because even if you don't have that much facility with this stuff, with iterated sums or the binomials, expansions or whatever, you at least know what it's trying to describe. You at least know in a concrete way where that's going, where that's coming from. It's less hieroglyphic. We've got that. It's just x plus h to the n expanded, written in this like very compact, terse, symbolic way. So we've got that, and then we expand that, which again, like, you know, maybe you don't have a lot of facility with like playing around with iterated sums, but we're just doing exactly what we've done now twice before, pulling out those first two terms, maybe evaluating the binomial coefficients, getting really the exact same thing we already had, just now with a bit more formalism. Same stuff happens, leading terms go away, you can divide through the h's. Big scary sum, there's at least one h in each of those terms, so then as we make things really small, we get just nx to the n minus 1. So we've got the full proof, the same proof, but we're not trying to do it all at once. We're not trying to do it, the full thing, start to finish, without any prep. We have this like progressive JPEG. Maybe that's the metaphor here. I also got a poster version of this proof, which you can't see because it's way too small and I couldn't figure out how to zoom and stuff on the PowerPoint, but I've got this full big like poster version of this proof where we've got these first four concrete examples on the top, and then the version with words, and then the version with iterated sum at the bottom, but showing in parallel every step. So it's easy to see sort of how things generalize and become symbolic. And if you want a written version, by the way, I've got some mathematical zines that contain this. 3 proofs of the power rule, which contains actually not just this proof, because this is just 3 passes of the same proof, but 2 totally different proofs of the power rule. So this could be yours for $0 if you want. I've got a bunch of them. So that's my first story of going off trail and perhaps bushwhacking in a somewhat nonlinear way toward the result. Second story, second example, is Taylor series. So Taylor series, ton of fun. It's one of my favorite things to teach in introductory calc. I think it's just a great sort of like narrative climax of introductory calculus for a lot of reasons. It's this like really cool result. You can turn anything into a polynomial, some fine print. The whole world is really just made up of polynomials. Cool result, great result, useful result. And what's equally cool as the result of Taylor series is the reasoning, is the sort of why Taylor series is true. The reasoning being that it's basically just integration by parts. You take an arbitrary function, rewrite it as the integral of its derivative, whatever, and integrate it by parts an infinite number of times, and you get a Taylor series, which is pretty cool. And then in sort of a big hand-wavy way, you've got this like really cool like storyline in calculus where we have like the product rule, and then we do that backwards, and we have integration by parts, and if we just do that an infinite number of times, we can turn anything into a polynomial, and it's this really cool narrative. So that's the big idea of why Taylor series is true. It's just integration by parts. There's some details, though. As a high-level description of why it's true, I think that's basically valid. But if you actually try to implement that story, it takes a little bit of work. So, first of all, kind of, yeah. So, first take I do on this, when I'm teaching this in class, is if you take the like really naive approach, take a function, rewrite it as the integral of its derivative, etc., integrate it by parts. If you do that in the way that you're probably used to doing as a kid taking intro calc and maybe doing a bunch of integrations by parts and having to choose which of the parts you differentiate, which of the parts you anti-differentiate, and doing that in the nicest way possible, you probably end up with just proving that functions are equal to themselves, which is true, but maybe not what you actually wanted to prove or find out. So, okay, it's a bit of a false start right at the beginning. So you can try again. And instead, if you make the same sort of argument, if you try to tell the same story, but just switch the parts, switch which parts are the derivatives, switch which parts are the antiderivatives. That's when it actually happens in a kind of more interesting way. And I'll say in passing, a little on time, but in passing, like another one of the things I love about this proof is it's just like funny. I don't think I've ever taught a proof where like humor is the theme. Because at every junction point, it's maybe a separate talk, but at every like decision point in this proof, you're sort of choosing the most ridiculous possible decision. You're choosing, for example, in this integration by parts, to do it in a way that ends up with this infinite series, which seems absurd, ridiculous. You're starting by taking a function, rewriting it as the integral of its derivative, which is, I mean, on the one hand, that's very basic algebraic step of things are inverses and whatnot, but it seems like ridiculous in another sense that we're taking something that's simple and making it more complicated. So humor is a big theme here in the proof, but anyway, integrated by parts in the less obvious way, and you end up with this Taylor series. Sort of. I give this story to the kids. The kids are, very happy to like do a bunch of integrations by parts. I don't want to be standing up there at the blackboard integrating my parts over and over. That's boring. But it's nice. They're good at integrating my parts, so I can just sort of set this up, and then they go off and they do a whole bunch of integrations by parts, and they end up with that Taylor series. That thing that kind of looks like a Taylor series. It's an infinite series. There are those like, x powers. There are some derivatives. And there are some like factorially denominators. kind of a Taylor series, but not really. It's not a Taylor series. It certainly looks a lot like it, but it's different in some pretty key ways. There's no constant term, for one thing. Maybe that's not a big deal. Maybe if we just did a definite interval, we would have gotten that, but there's no constant term. There are these weird, like, alternating signs, which isn't really what we want. And then maybe most importantly, this thing we got isn't actually a polynomial. This thing we got is, well, we have all these, like, original derivatives. So if underlying derivatives aren't polynomials, then that whole thing isn't. And I'll say, like, when I've taught this, I've usually split it over like 2 days, maybe like 2 75-minute class sections. And this is how we usually try to end the first day, on this like weird cliffhanger. We've done all this work. I've been telling this like exciting story about how we're going to get a Taylor series, and blah, 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 and we end up with this thing which is like clearly not like completely wrong. It's somewhere in that vicinity, but also is like very definitively not what we actually want. So let's try again. Take number 3. And we talk about how we want to change the proof, refine the proof, things we do differently, and set things up, and we'll do a definite interval instead now, and maybe we can use like the fundamental theorem of calculus and rearrange things, and that, like, if we do that, we like very quickly get a constant term, and so that's nice, and then maybe then we just like proceed with our integration by parts. Kids are very happy to do that. It's even more work, because now you got to subtract and stuff. Take number 3 doing this, and we get a Taylor series. Except, again, not really. We've got this thing that now looks a little bit more like a Taylor series, maybe, but is still very definitively not what we want. We've still got these weird alternating signs. The C is coming up, but in these weird ways. So actually we have to do this like a 4th time now, and make one more refinement, which is to use this weird antiderivative when we're integrating by parts. And I've had a couple of kids actually come up with that antiderivative by like basically like thinking about what they want and trying to think about canceling things out. I've never pushed it that hard because, I don't know, I don't think I would be able to come up with that if I, were just doing it from scratch. But we do this a 4th time, and by this point the kids are just kind of like burned out, and they're discouraged, and they're like just waiting to be let down again. How am I going to once again break their hearts? But they do all the integrations by parts and end up with actually a Taylor series this time. Takes 4 tries, but they've actually ended up now with a real Taylor series. This big overriding story of Taylor series being integration by parts is basically true, but also the details matter. And we can sort of explore all these ways, make these false starts, and eventually get to the right answer. So, almost out of time. But maybe then the moral of the story. Hiking on trails is hard enough, and I want to be compassionate here and say that I don't want to demean anyone who wants to hike on trails, because that's genuinely often enough of a challenge. But if we want to really understand the landscape, if we really want to have sort of a full feeling for the environment and its texture, its shapes, whether that's the environment of Wyoming or whether that's the environment of abstract mathematics, maybe we should try a little bit more bushwhacking. If you want to see either of these proofs in more detail, they're on their website. I've got them written out very nicely. Thank you. And if you want a zine, come find me. I've got a big stack of them.
Thank you very much. Thank you, Andrew.